Thanks everyone for joining us today. Today for our Otter Talk, we've got Michel Alexis, who's going to talk about BiLipschitz instability of weighted norm inequalities for singular integral operators. So take it away.
All right. Well, thank you very much for the introduction, Meredith. I'm very happy to be here to talking to you guys, a different audience that I normally talk to. And so yeah, I want to talk to you about this notion of BiLipschitz instability for singular integral operators for weighted norm inequalities. And the work I'm going to talk about, or give you the context of and talk about a little bit, is joint work with my fellow co-postdoc Jose Luis Luna Garcia, my postdoc mentor Eric Sawyer, and our frequent collaborator Ignacio Urtituero. And so this is just something that we've been thinking about for the last throughout the large chunk of 2022, basically. So what's my favorite operator? And hopefully for some of you, your favorite operator. Well, mine is the Hilbert transform. So how is it defined? Well, you look at the Hilbert transform of the real line. You take a function f. How's hf defined at x? Well, you look at f of t and you integrate against x minus t with respect to dt. Of course, one of the things that we know is that this is not well defined, right? If you ask if h is well defined, this doesn't make sense, right? The kernel 1 over x minus t is not integrable, so it doesn't make sense to evaluate this integral. What you need to do instead is take advantage of cancellation. What you need to do is you need to integrate away from the singularity when t equals x, and what you want to do, you integrate an epsilon away from that singularity, and then let epsilon go to 0, and you hope that by the kernel on the left side and the right side of x cancel each other to give you some sort of concrete value, right? So the point I want to drive home here is that to make sense of the Hilbert transform, cancellation is essential to make sense of it. And so you see this in practice. How does the Hilbert transform act on functions? Well, if I look at an indicator function for a function f, what does the Hilbert transform of the indicator look like? Well, at the part where f is flat, you're gonna have like pretty much perfect cancellation. So your function will be small. But when you get at these jump off points, at these points of discontinuity, the Hilbert transform is going to transform those points of discontinuity into singularities because you don't have a proper cancellation at these endpoints just when you compute this integral. Okay. The point here is that the Hilbert transform will take discontinuities and blow them up, or take ridges and blow them up, right? So why am I talking about the Hilbert transform? Well, this is kind of a prototypical example of what we call a Calderon-Zeigman operator, right? So what's a Calderon-Zeigman operator? So we're going to say an operator T is a smooth Calderon-Zeigman operator if it acts on functions by integration against a kernel, and where that kernel is smooth, and it's going to satisfy some decay conditions. In particular, what decay conditions am I going to ask it to satisfy? Well, I want that the kernel, let's pretend this j equals 0. I want the kernel to be controlled by 1 over x minus y to the n, where n is the dimension. That's the same as the Hilbert transform. And I want the derivatives to look similar. If I take j many derivatives, I get j many extra powers of singularity. Okay. And I need some continuity condition, which I won't get into, but the point is that we have the size condition or decay condition on the kernel, which looks like the Hilbert transform. If you ever get lost in this talk, just go back to the Hilbert transform. That's our main guide. So what are examples of Calderon-Zeigman operators? Well, like I said, the Hilbert transform, we have the kernel k, which is 1 over x minus y, and it satisfies all these conditions. As you take derivatives, you just get higher and higher powers of the singularity. The Riesz transforms are another example, right? If I go to higher dimensions, I have what are analogs of the Hilbert transform, which are the Riesz transforms, where the Hilbert where now I have cancellation along one direction, right? So if I take the jth direction in Rn, I do xj minus yj over x minus y to the n plus 1. If I integrate this against a function f, I'm looking for cancellation in that jth direction. Okay. So think of it as Hilbert transform along a direction. It's not quite true, but it's morally what you should think. And then finally, something that maybe more relevant to this audience here, right? The Berling transform on the complex plane is also a Calderon-Zeigman operator, right? You have k of z. The w is the kernel is 1 over z minus w squared, where of course you have to make sense of everything using a principal value or letting epsilon go to 0 in some way. Okay. So why should we care about the Hilbert transform? Well, again, something familiar to, I think, this audience. If you have a real valued function on the real line, well, one question you can always ask is f the real part of some analytic function on the upper half space? And that turns out to be true if f has sufficient decay, right? In particular, you can take what looks like a Cauchy integral of f. You do f of t over t minus z. You integrate over all of r, and for a fixed t, that will you can define this capital F of z, and this capital F of z turns out to be analytic on the upper half, right? So it'll be analytic all the way over here, and furthermore, if you take a z equals x plus iy and you let y go to 0, meaning you approach the boundary, then it turns out that the boundary values of your capital F turned out to be, well, the real part will look like f, maybe up to a constant, and then the imaginary part will look like the Hilbert transform of f up to some constant again, right? So this is just context for, I think, that some people already have, but just reminding you of like why we should care about these operators, right? They kind of pop up in a natural way with respect to complex analysis, among other things. Okay. So one thing you can start wondering about is how does the Hilbert transform act on functions? So remember, so I'm a harmonic analyst. My space of functions that I enjoy, which I think a lot of people enjoy, is L2 space, right? The Hilbert space of the Hilbert space L2. But remember, it has norm what? You take f, you square it, you integrate it, and then you take the power 1/2 for homogeneity reasons. And if that's finite, you say f is an L2 function. So L2 is the vector space of these functions. And one of the first theorems you learn when learning about the Hilbert transform is that the Hilbert transform is a bounded operator from L2 to itself, meaning in particular there's some constant for which the Hilbert transform of a function in L2 is controlled by the function itself in L2, norms, of course. In this talk, we're only going to be concerned with what I'll call nice Calderon-Zygmunt operators. What do I mean by nice? There are going to be Calderon-Zygmunt operators T, which are bounded on L2, and they're going to have non-degenerate kernels. In particular, I don't want to consider the 0 operator. I want the kernel to have that singularity. I want it to be just barely integrable. Okay. What are examples of nice Calderon-Zygmunt operators? Well, think Hilbert transform. That's our main example. Riesz transforms, which are the higher dimensional analog. Berling transform. These are all nice in this sense, non-degenerate, and they're bounded of L2 to L2. Okay, so you can ask the following question: when does the Hilbert transform take bounded from measure space L2 of a measure to L2 of that same measure? Right. For which measures do you have the Hilbert transform is bounded from L2 of mu to L2 of mu? Well, Hunt, Mook, and Halbweden in the 70s were able to show the following. The Hilbert transform is bounded from L2 of mu to L2 of mu if and only if mu is absolutely continuous, meaning it's some weight w of x dx, and this weight w of x has finite A2 characteristic. Where what is the A2 characteristic? Well, it looks like the following. You take w, you take its average over a cube or interval. You take the average of w inverse over that same interval. You multiply the two, and you see the largest that can be. If that's always bounded by some constant, then you say your weight is A2, right? The same is, and I claim this theorem, this is the same for any nice Calderon-Zygmunt operator, right? You just do the same thing in higher dimensions if you're in higher dimensions. But the point is you start with you have boundedness of your operator if and only if this condition about the measures holds. Okay. I just want to emphasize off the bat, this is a great theorem, right? The Hilbert transform involves lots of nasty cancellation things. It's annoying to kind of evaluate the Hilbert transform except on certain types of functions, right? But the fact that the boundedness of the Hilbert transform boils down to something just about the weights, where there's no cancellation required, you're only dealing with positive things, that's great for like a harmonic analyst like myself, right? I love estimating positive things. That's kind of my bread and butter. That's the ultimate that's the ultimate sort of correspondence or if and only if condition, right? I don't need to estimate any sort of nasty cancellation, anything that requires nuance. I can be straightforward about this. How easy is this to work with? Well, you could give this as an exercise to any of your better calculus students, right? They could if you're on the real line, you can show that a power weight is satisfies the A2 condition if and only if your power is between -1 and 1, if you're on the real line. But the point is, this is also something that all of you could work out like fairly easily. Like it does not take that much time. Okay, so great. We know how the one weight problem works. Now you might wonder, how does the two weight problem work, right? So in particular, let's say I want to understand pairs of weights omega and mu, for which the Hilbert transform is bounded from one L2 space to the other, right? Well, you go ahead and stare at this question for a while, as people did in the 70s and 80s, and one thing you realize, this is a little bit ill-posed, right? We should kind of, to simplify our lives, we should kind of pose this in a more correct way before proceeding. So what do I mean by this? Well, I mean the Hilbert transform. This looks like an integral of f against the kernel x minus 1 over x minus y. And the measure I'm integrating with is dy. On the other hand, for this, to make sense of this norm inequality, I'm thinking of f as being mu measurable, right? So in particular, whatever measure f is measurable with respect to, I should also integrate against for the Hilbert transform, right? It doesn't make sense if mu is a bunch of point masses, right? F is maybe only defined on a finitely many points. Then if I do the Hilbert transform of f, maybe it's 0 everywhere else I get a 0, right? This question doesn't quite make sense. So what we want to do, we want to restate this problem in a way that where we have the same measure out here and inside the Hilbert transform. So let's just pretend things are nice, and let's see what the appropriate restatement of this should be. So let's pretend mu is an absolutely continuous measure. Let's say it's mu of x dx, right? So we have this mu here. And let's replace f by f sigma, where what is sigma going to be? I'm going to take that as nu inverse, right? This is true for we want this to be true for arbitrary functions f. So certainly if I replace f by f sigma, this should also morally be true. Now what do? Let me kind of expand things out. Let me bring this sigma squared outside, multiply by against mu. And what do I get? Sigma squared is nu negative 2 times nu. I get a nu inverse, which is just d sigma. Okay? And so now, lo and behold, I have sigma on the outside and sigma here. And so now I claim this is the correct version of the two-weight norm problem, two-weight norm inequality, right? I want to find characterizations of measures sigma and omega such that the Hilbert transform with this sigma tugged in, this h sub sigma, which I'll define h sigma of f is the integral of f against d sigma with the kernel 1 over x minus y. I want to see when this is bounded from L2 sigma to L2 omega. This is the correct sort of statement of the problem. And you do the same rescaling for all sorts of all the other nice Källner-Zeigman operators, and you want to kind of address this question. And one thing that starts to pop up as you start addressing this question, you can come up with the two-way analog of the A2 characteristic. In particular, this is what we call the A2 condition, the two-way A2 condition. Right? You take the largest average of one measure. You take the average of one measure over a cube. You take the average of another measure over the same cube. You see the largest that product can be, and if that's finite, you say your measure satisfies the A2 condition. One thing that changes now in the two-weight world, as compared to the one-weight world we had before, is that this two-weight A2 condition no longer implies norm boundedness. Contrast this to the one-weight world, where we had an if and only if statement. Your norm boundedness was equivalent to the A2 characteristic in one-weight world. Two-weight world, that's not the case. Okay. So what do you have to do to try to get a characterization of when this norm inequality holds? Well, you have to go with a characterization that's a little bit harder. What you end up having to do, or at least what's most known right now, is the Sawyer testing conditions. So you have the following theorem for the Hilbert transform, proved by Lacey, Sawyer, Shen, Uriarte, Tuero, and then a second part by Lacey in 2012, the two-part paper, which goes as follows. Assume your measures omega and sigma don't have common point masses, and assume that there's a stronger A2 condition which holds, where the two-way A2 condition, where instead of taking averages of your measures, you take Poisson averages, so something involving tails, but morally averages. Then you have norm boundedness of the Hilbert transform for all f, if and only if you have this following obtuse thing, what we call testing conditions. where you take this inequality, you replace f with an indicator of a cube, and you want this to hold for all cubes, and maybe you place indicators of cubes outside here, right? These indicators on the outside, these aren't so important. The moral here that you want to remember is that the norm inequality holds. To get the norm inequality to hold, it suffices to kind of check it for just indicators of cubes. That's what this statement is saying. You want the norm inequality to hold? I just need to test across cubes, which is why it's called a testing condition. Okay. For general nice Calvin-Zygmunt operators, it turns out you have similar statements if the measures are regular enough. So what do I mean by regular enough? Well, in this case, it's going to mean doubling measures. So what's a doubling measure? Well, a measure on Rn is said to be doubling if you take the measure of a ball. This will always be controlled by a measure of the same ball, of the ball with the same center, but half the radius. In other words, doubling measures are kind of locally regular, right? They don't change too much from one ball to another. If they change, it has to happen with like various scales. Okay. The point is this rules out things like delta masses. Okay. So with this in mind, myself and Eric and Ignacio Uriarte-Tuero, in 2021, we were able to prove the following testing theorem, which is, well, the testing theorem, like I mentioned above, holds for all nice Calvin-Zygmunt operators, so long as the measures sigma and omega are doubling, right? So if your measures are regular enough, you get the same sort of statement of, to check the norm inequality, it suffices to check the norm inequality for f equals indicators of cubes. And then in 2022, Eric Sawyer and Brett Wick were able to extend this theorem in a more technical. We're able to make what do I want to say? They were able to extend this theorem to LP rather than L2. What happens in LP? Well, the statement of the theorem is more technical, but kind of in the same spirit, where to check the norm inequality for functions f, it suffices to check it for indicators of cubes, but there's a little wrinkle there, which I won't get into. The point is there's a variety of theorems of this flavor. And here again, they had to assume sigma and omega are done. Okay, let me pause for a bit to let people digest and process. I will chug some water and then ask questions if questions come up before I continue. Okay. So I gave a bunch of I threw a lot of information your way. So let's just kind of synthesize and process what's going on. Okay. So we have one weight versus two weight problems. We have one of these involves an A2 condition, and the other one involves kind of testing being the primary characterization. In the one weight case, right, your A2 the A2 characteristic holds if and only if your operator is bounded. Right, this was some nice condition involving the weight, if and only if operator is bounded. Very nice. In the two-weight world, the analog of the A2 condition can't characterize boundedness of your operator. It turns out only testing can. Only testing conditions can. On the other hand, this is kind of a little unfortunate, right? Because testing can be hard to check, right? For testing, this still involves the operator. And the operator usually involves cancellation. Think back to the Hilbert transform. It involves cancellation. So in order to verify testing, you need to delicately estimate cancellation of your operator, acting on indicators of cubes, but also involving exotic measures, right? You could have a measure that's very singular, and evaluating the Hilbert transform against some exotic measure, it seems like it could be difficult, like example to example, right? It's a varying difficulty. Versus checking the A2 condition, that's just, you can estimate things by above, you can be very brutal and still show that the A2 condition holds. Right? Everything's positive in the A2 condition, and the averaging integrals are simple. But so now let's think a little bit more about like what's so nice about the A2 condition, right? I claim also the A2 condition, it's very robust. If you dilate your weights, the A2 condition will still hold, right? If you translate your weights, that makes sense, they'll also still hold. But I also claim that they're stable under BiLipschitz change of variable, meaning if you take two measures sigma and omega, you do a change of variable, a BiLipschitz change of variable, and then you look at these new measures, sigma star, omega star, I claim the A2 condition will also hold if it held for the original weights. So it's very robust. So what I'm going to say that the A2 condition is stable under BiLipschitz change of variable. If it held for some pair of weights, I do a BiLipschitz change of variable, it still holds. And so what this means by this implication right here, well, A2 holds only if and only if your operator is bounded in the one weight case. Well, that means that one weight norm inequalities for singular integral operators are BiLipschitz stable as well. This is not the case for two weight norm inequalities, right? One thing we discovered as we were kind of looking through this, there was an easy example from 10 years ago in a paper by Alexis, Eric Sawyer, and Ignacio Urartetuero, which goes as follows, right? There exist measures sigma and omega and a BiLipschitz map phi such that the norm inequality for the Hilbert transform holds with respect to sigma and omega. But then if you perturb sigma and omega by a BiLipschitz map phi, meaning you do a push forward, the Hilbert transform is now not norm bounded with respect to these new BiLipschitz push forward measures. Okay. So with this in mind, let's kind of see a vague idea of what this looks like. Okay. So let's see. Let's look at their example. So what does their example involve? Well, their example is going to involve the Cantor set E, and we're going to define Cantor measure sigma on the Cantor set E. So what is the Cantor set? Well, remember, you start with the unit interval 0, 1. Then you remove the middle third. So I get 0, 1/3, 2/3, 1. Then I get, I remove another middle third. And I keep going, so on and so on. And what's the measure sigma going to do? Sigma is going to take, at each generation, it's going to assign equal measure to all of these intervals, right? And it's going to have total mass 1. So in particular, it's going to assign this measure mass 1. How do I assign it mass 1? Well, I'm going to say this has mass 1/2, this has mass 1/2. How do I say this guy has mass 1/2? Well, I'm going to say this has mass 1/4, 1/4, 1/4, 1/4, 1/8, 1/8, 1/8, 1/8. And you keep going. That's what my Cantor measure is. And what am I going to do with this? Well, first thing I'm going to do, let's graph H acting on sigma. Okay. So I have, what I do is I want to evaluate at a point x, I integrate d sigma against 1 over x minus y, where x is my point that I'm fixing. Well, let's think about what's happening. Y lives on the support of the Cantor measure. So if x approaches the boundary of the support of the Cantor measure, then this singularity is going to become more and more prominent, and I'm going to get a blow up here. So in particular, as x approaches this left boundary, I'm going to get plus infinity. As x approaches this right boundary here, I'm going to get negative infinity. I'm going to get singular behavior at both sides, right? And then just a little sign change. And what's going to happen? Well, in these next middle thirds that were removed, I'm going to get the same behavior. I'm going to get plus infinity minus infinity, plus infinity minus infinity, and you keep going. And you have this self-similar process. You know, you're going to get a bunch of these graphs, okay? And so now, what am I going to take as my other measure pair, omega? What I'm going to do, I'm going to take it to be the sum of delta masses at the zeros of H sigma, right? In every middle third, by this picture, you can see that there's a 0 just by the mean intermediate value theorem, okay? So what I'm going to do, I'm going to take omega to be a bunch of zeros, right? These are my, or a bunch of, it's going to be a bunch of delta masses at the zeros of my Hilbert transform acting on sigma, okay? And in this case, you can check that, for instance, the Hilbert transform acting on sigma, if I take the LP norm of this with respect to omega, it's equal to 0. In particular, sigma and omega don't really see each other when mediated by the Hilbert transform. We chose our delta masses to satisfy this. And with this in mind, you can then show that H sigma is bounded from L2 sigma to L2 omega with relatively small norm. Okay. Now what we're going to do, let's do the following. Let's take our point masses and let's shift them to the blow-up points of H sigma on each interval, okay? And I'm going to do this via BiLipschitz shift. I'm just going to move all these a fixed proportion in each of the middle thirds interval. And what's going to happen is that as I move these guys, all omega is now a sum of delta masses at the blow-up points of H sigma, okay? And now what do I want to say? As omega is seeing all the blow-up points of H sigma, I then get this is equal to infinity. I can cherry pick things so that this integral is equal to infinity, actually. And so in particular, you have H sigma, which is no longer bounded from L2 sigma to L2 omega. Okay. And so morally, like, how should you think about this? This is kind of the first example of why you need to characterize the norm inequality with something that is BiLipschitz unstable, right? You see this example, you see BiLipschitz instability, which means that a very clear instance of BiLipschitz instability, which is why you need testing. You need to characterize the norm by something which is BiLipschitz unstable. Again, I've thrown information your way, so let me pause for a little bit of digestion and let me drink some water. Okay. If no one has immediate questions at the moment, let's continue. So one thing you might ask about this BiLipschitz instability of the two-weight case versus the one-weight case is you might wonder, like, okay, how far does it go, right? If I'm the devil's advocate, I say, like, hey, this BiLipschitz instability stuff, it feels pretty manufactured in the previous example, right? You place your masses exactly at the zeros, like, this feels like cheating somehow. This doesn't feel like generic behavior. Maybe there's a simple condition which will rule that sort of example out that I gave you in the previous case, right? Like, what if we restricted ourselves to a class of more regular measures? And so, yeah, you can do that. I claim you can do that, but you're going to need some pretty strong assumptions, right? So in particular, we're wondering, like, what can I do to fit in within this this class of BiLipschitz stable pairs? Well, the following thing you can do, you go through the literature and you reinterpret estimates with this BiLipschitz instability in mind, and you see this theorem of Houghton and Lacey in 2012, which, when reinterpreted involving BiLipschitz stability, says that if T is a nice Calvin-Zygmunt operator, then the norm inequality for T sigma is BiLipschitz stable for pairs of A infinity weights. What is an A infinity weight? I'll get to that in a moment. But the point is that, like, within the BiLipschitz stable pairs, we have A infinity pairs, which are sitting down here. And I claim these are very regular measures, like maybe more regular than you would like. So what are A infinity weights? Well, first let me define an AP weight. So this is similar to the A2 characteristic. You're going to say W is an AP weight. If you take the average of W, you take the average of some negative power of W, you multiply them together, you with some extra power here, don't worry too much about it, and you see the largest that can be. And if that's finite, you say W is an AP weight. And you're going to define A infinity as just the collection of all AP weights. It's just the union of all AP weights. Okay. I claim this is a very regular class of measures, a very regular class of weights. How regular? Well, the first thing is that AP weights are absolutely continuous, right? That's just kind of, in some sense, by definition, right? I chose absolutely, by definition, I chose them to be absolutely continuous, but that's already excludes a lot of singular measures. The next thing is that this condition, this is vaguely saying that your weight W should be constant at all scales. I won't get into that too much, but that's just something that you, if you want a little brain teaser, you can kind of think about what that means with respect to this to this condition. But it's saying, but this condition is saying vaguely that W should be constant at all scales, and what that vaguely says as far as growth is that W can't be too singular or oscillatory. Furthermore, AP weights satisfy a reverse Holder inequality, right? If I if I take a weight W, I raise it to the power to a power greater than 1, I take its average. That's going to be controlled by the average of W to the power 1. This is usually the opposite of how you expect things to go. Holder's inequality says you can go from here to here. You can control this by this. The fact that it goes the opposite way tells you that these are, like, on the one hand, this is beautiful to work with these weights, but not many weights are going to satisfy this condition, right? And then finally, if W is an AP weight, then W also happens to be a doubling weight. So the picture I want you to have in mind, you have A infinity weights, which are contained within the set of doubling weights. And these are in turn contained within general measure pairs. And I want you to think, like, these guys are relatively small. There's not that many weights which are that regular. It's nice to work with them, but there's not that many. Okay. So, and then, yeah, like, what do they look like in practice? Well, they can have zeros and singularities, but they can't be too deep, right? And that's just the result of this condition. Okay. So again, devil's advocate comes back to me and says like, okay, fine. If I assume a lot of regularity, I can obviously get BiLipschitz stability, right? If I make strong assumptions, I can get a strong conclusion. But there's got to be a way to weaken this, right? Like should be able to weaken the notion of A infinity to get something non-trivial, which is a BiLipschitz stable. Or I shouldn't say non-trivial, but something weaker, that it's more ubiquitous, right? Can I get a more ubiquitous class of regular measures, which are BiLipschitz stable, right? And if you're a harmonic analyst like myself, the first thing you think of is doubling measures. These are kind of like the building blocks of our harmonic analysis. If I can work with doubling measures, that allows for somewhat singular behavior and yet well-controlled behavior. This would be a reasonable middle ground. Unfortunately, these are not BiLipschitz stable. So this is work done by myself, Jose Luis Luna Garcia, Eric Sawyer, and Ignacio Uriarte back in August, and we showed the following: if you take an individual Riesz transform Rj, and if you give me a small parameter epsilon, then I can find an angle theta less than epsilon and doubling measures sigma and omega, such that the norm inequality for that Riesz transform holds with respect to my measures. But then if I rotate them by angle theta, they no longer hold. Rotate them in a special direction. In other words, not only do you not have BiLipschitz stability, you lack even rotational stability. You can have a pair of measures where the Riesz transform is bounded. You rotate them a little bit, all of a sudden you're unbounded. Zero. So I should put a little asterisk here. This is phrased as far as a qualitative statement to kind of make it more palatable. Technically, we did not prove this. We proved a quantitative version of this, but such a broad quantitative version that like one would not it's the most broad quantitative version you could imagine. Okay. But so now what does our picture look like? Well, you have BiLipschitz stable pairs. You have A infinity pairs, which are sitting inside like the core of an avocado. And you have doubling measures, which will intersect by some doubling measures will be BiLipschitz stable, right? In particular, A infinity pairs will be in there. But you have lots of doubling measures, which won't be. Okay. And so just one thing I kind of want to synthesize before I move on is just that the set of BiLipschitz stable measures is already a lot smaller than I would have thought. I think it's a lot smaller than a lot of people would have thought. But then how small is it? Well, that's kind of unclear, right? Finding the precise dividing line here of what's the class of BiLipschitz stable measures, it's unknown at the moment. So certainly it's an open problem. If this interests anyone, certainly have at it. Like I would be very, very interested to see what people come up with. Okay, so I want to talk about this theorem. And so first I want to start with just a very big picture of what's going on, right? So how do I get rotational instability for doubling measures sigma and omega? Well, what's the big picture? The big picture is that we construct measures that look like sheet metal, right? So imagine sheet metal, it's constant in one direction and it's corrugated in the other direction, right? So what do I do? Let me start with the Riesz transform R2. It points in the vertical direction, right? All of its cancellation is happening in the vertical direction, right? But because my weights are constant in that vertical direction, it's not going to see all that cancellation is going to cancel out nicely. I'm not going to get any sort of bumps or singularities or anything of the sort. But now what you do, if I rotate my weights, that's rotating the sheet metal. That's the same as rotating R2. That's the same as rotating this arrow. If I rotate this arrow, even just a little bit, I start to see all those waves and bumps that the cancellation then sees and says like, hey, I'm going to have a bunch of blowups here. If you rotate R2 slightly, it sees all the ripples all of a sudden, and then you get blow up immediate. Okay, so that's the big picture idea. So again, I throw it in a lot your way. So let me pause for questions, thoughts, concerns before I get into what are the more technical things in the last 10 minutes of this talk.
Hi, Michel. Can you hear me?
I can hear you loud and clear.
Hi, so I have a question. I don't know if it's a good moment. So I miss in the set picture, right? Maybe the previous slide, right? It's so. Do we know that any BiLipschitz stable pairs which is not a doubling?
So yeah, so there are examples of weights which are called weak A infinity weights, which Yeah, which are basically, if I go back to, right, all A infinity weights will satisfy a reverse Holder inequality. Weak A infinity weights will satisfy a reverse Holder inequality for where what you have here, you don't have Q, but you have 2Q, the dilate of Q, basically. And those weights, there are some which are not doubling, in which case in this picture they'll kind of they would kind of like live here a little bit. They would not be doubling, so they would not be in here. They would not be doubling measures, so they'd kind of live out here. But they're just slightly weaker than A infinity weights.
Okay, great. Thanks.
Yes. Does that answer what you're wondering?
Yeah.
All right. Lovely. Okay. So we have about 10 minutes, and there's I put on slides a bunch of technical things that I obviously will not have time to go through. And I'm going to say a few technical things, but don't, just focus on one or two things at a time, like don't worry about absorbing everything. I just want to paint like broad strokes a picture of what's going on. So what's the medium level idea of how to construct these doubling measures? So I gave you the big picture example. How do you do this? How do you do this in the weeds, right? Well, the first key step involves thinking about just the one-dimensional case, thinking about the Hilbert transform, and you want to create doubling weights which are badly behaved for the Hilbert transform, right? You want to create weights which have this sort of waviness, this corrugatedness, like the sheet metal. And the way you do this is you follow the ideas of this guy Fedor Nazarov. He had a very lovely paper telling you how to do this, right? So what you do, the key steps, is you first construct weights on the unit interval, sigma and omega, which are ill-behaved with respect to a discrete operator. So not the Hilbert transform. The Hilbert transform is continuous. But you start out by creating weights which are badly behaved with respect to a dyadic operator. And why do you do this? Well, dyadic operators will often serve as sort of a litmus test, a threshold marker for bad behavior for Calvert-Zeigman operators, like the Hilbert transform or anything else. It's not always the case, but there's some relationship where you can't say one implies the other, but there's some sort of deep tied relationship, right? So what do you do after this? You have weights sigma and omega, which are cherry picked to make a dyadic operator behave badly. But now what do? We're going to do what's called a transplantation argument. What you do is you break sigma and omega into their key frequency parts, right? Sort of like a Fourier series, but not quite. But think like Fourier series. And what I'm going to do, I break them up into their various key frequency counterparts, and I'm going to space out all those frequencies. I'm going to take that same data, but then space out all the key frequencies so that they don't really interact with each other. In particular, what this does is this localizes the action of the Hilbert transform on each one of those key frequency pieces. Okay. And then finally, to make that sort of localization precise, you have to use complex analysis involving the Hilbert transform to recover the data associated to each frequency. And then from there, when you act on the Hilbert transform, you recover the ill-behaved data from the dyadic operator, the discrete operator I had before. What do you do? So that's nice all in dimension 1, but I promise you BiLipschitz instability involving rotations. So I've talked to you about dimension 2. What do you do with dimension 2? Well, you tensor your weights with just the constant function so that you get sheet metal weights. And then what do you do? Well, to show that these weights are ill-behaved, you have to show that they're ill-behaved for the Riesz transform R1, the horizontal guy, by saying their behavior is the same as the Hilbert transform. But then on R2, you have to argue that things are well-behaved because R2 does not see any of those ridges. R2 just sees constancy. Okay, so I won't necessarily go through all this, but kind of what I want to bring you, the journey I want to bring you on in these last few minutes is vaguely about this idea of localizing in frequency. Okay, so let's pretend that step 1, we create some weights which behave badly with respect to a dyadic model, and you can do this and ensure that your weights are what we call dyadic doubling, and you can do this using an argument of Nazarov. This, by the way, this is the only way I know of to kind of get dyadically doubling weights. And by dyadically doubling, I mean with respect to sort of these particular intervals, which I won't get into too much. But assume you have your weights which are badly behaved for a discrete thing. How do I go from discrete to continuous? Well, what you do is you're going to rearrange your weights. So assume you have a weight W0, which is badly behaved for a discrete operator. And what I want to do, I want to look, the way I can always look at a weight is I can look at its averages, right? Maybe, so in this picture, I have an initial weight created for my discrete operator, W0, and I'm going to let colors represent averages of the weight at various levels. So maybe this is average 1, maybe this is average 1/2, average 3/4, 3/2, and then these are all various different averages that I'm just representing by colors because it looks nice. What am I going to do? Well, to get something that's badly behaved in the continuous world, I'm going to take these averages and space them out. What do I mean? Well, I'm going to define a weight W1 from my initial weight W0. I'm going to make it have the same exact average at the top level on 0, 1 to be the same average. Then what am I going to do? Well, I want to preserve the same average values of W0 at lower scales because that's sort of the key data encoded by W0. But what I'm going to do, I'm going to increase the frequency with which these averages occur. So in particular, I'm going to take this average purple and red, and I'm going to have them occurring at smaller scales more and more often. So I'm going to oscillate purple, red, purple, red, purple, red, purple, red, purple, red, etc. Okay. And the point is, like, maybe the difference in scale from here to here is maybe I divided by 2. Here I'm dividing by 8 or divide by 16. I'm divided by some large power of 2. Now, what do I do? Well, for a purple guy, and now this breaks up into an average guy, into a weight which has averages on the left side, which are blue, averages on the right side, which are yellow. And what I'm going to do, I'm going to do the same thing. I'm going to repeat blue, yellow, blue, yellow, blue, yellow, blue, yellow. For the red guy, I'm going to do green, brown, green, brown, green, brown, green, brown, and back and forth, back and forth. What I'm going to do is I'm rearranging these weights, and I'm kind of interspersing all the different averages. And I'm getting something that looks a little fractalish and a little singular, right? And I keep on doing this for each one of these subintervals, right? I get pink. If I zoom into the blue down below, I'm going to get pink, gray, pink, gray, pink, gray, pink, gray. Okay. So besides being complicated, why do I care about this, right? What does this get me? Well, think about the weight on the left side, right? I can write this as the expectation. I can write it as the average of its top level, right? That's this expectation notation, expectation of 0, 1 of W0. And then plus, well, how do I characterize the rest? Well, I have to talk about how much this average deviates by this one. If this black is average 1, this guy has average 1/2, and this has average 3/2. That means, how do I get from here to here? Well, I subtract 1/2 here, and I add 1/2 here. Okay? What that boils down to is that you're adding a constant times a hard wavelet, where a hard wavelet is -1 on the left side of an interval and +1 on the right side of an interval. And so what you can do, you can take your weight W0, you break it into its average value at the top, and then a bunch of hard wavelets localized to each one of these guys, right? So this will be -1 + 1, -1 + 1, -1 + 1, multiplied by all different constants, okay? And now what's happening on the transplanted side? What you're doing is you're taking these hard wavelets, which kind of have a certain base frequency, right? This repeats itself just at frequency at scale 1/2, and you're increasing the frequency of these guys. You're increasing them a lot. Now, all of a sudden, something that just had one period now has like 4 periods in the same interval. And then the next transplantation takes this guy, which has a period of 1 period on an interval of size 1/2, to now it has a period 2 to the 10, or it repeats itself 2 to the 10 times on an interval of very small size. So we're increasing frequency here. And what that's doing is we're on the one hand preserving the initial data of the weight W0, but we're drastically changing the scales of all the various frequencies of W0 to where they are well localized. They behave, they don't really see each other. There's such different frequencies that when I act on them by the Hilbert transform, things will behave quite all right, and you won't see anything. And yeah, maybe in the last 10 seconds I have to kind of say something. I'll say the following. In this construction, as you get these oscillating terms, you're going to get what you get a weight W1, which looks like average at the top, plus a sum of oscillating guys. So maybe constants times SKIs, where these SKs oscillate a lot. One of the key things is that if you look at the testing conditions for the Hilbert transform with respect to sigma and omega, you use this expansion, you get this looks like Hilbert transform acting on a bunch of oscillating functions, and you need to estimate these appropriately. How do you estimate these appropriately? Well, it turns out the only way to really do this is using complex analysis. You can get certain estimates without complex analysis, but I claim what it boils down to is complex analysis of the Hilbert transform. There's no real way around this. So what do we do in our case? Well, in our case, we took one-dimensional weights and we tensored them in, with constants in the vertical direction. But now we have to look at the Riesz transform acting on our new weights, right? This boils down to then you have to estimate what the Riesz transform looks like on tensors of these oscillating functions. So they're horizontally oscillating and vertically they stay constant. And what did we do? Well, the only thing we can do is really go back to the Hilbert transform. So we say the Riesz transform acting on this tensor looks like the Hilbert transform tensor, the constant direction. And then the Riesz transform acting on the vertical Riesz transform acting on the horizontally oscillating functions goes to 0. Okay, that's all I have to say. Thank you so much for your time and patience and mental energy.